Hi everyone, this is Adam again. So the last video I went through the first bit of probability, so I'm just going to finish that chapter now, which is kind of on like relative frequency, and then how do you get into like some sets with probability, and things like that. So I'll just do one example, and then I think I'll leave it at that. So what is relative frequency? So there's a formula for relative frequency. This is basically just the number of times an event happened divided by the total number of trials. This might sound a little bit weird, but like it'll be very, obvious in a second. So basically, one of the things here is going to be, so say heads and tails. Okay? And basically they're just asking, they're saying, okay, well, here we have a table. This is after 10 flips, after 20 flips, after 30 flips, after 40 flips, and then after 50. So basically, I'm just going to put in data here. So we get 6 heads and 4 tails, then we got 13 and 7, then we got 13 and 17, we got 18 and 22, we got 24 and 26. So this is basically, this is just some data. So it's just you're flipping a coin. How many times did it land on heads? How many times did it land on tails? Something like that. Okay. So here it says, so first of all, let's work out the relative frequency of heads after 50. Okay, so actually, I might just do the relative frequency down here, actually. Might be a little bit easier. So the relative frequency for the first one, so for heads and tails. So for the first one, I have 6 heads out of 10 goes. So the relative frequency is just 6 over 10. Okay, that's it. And then for tails, it's just 4 over 10. For the next one, it's going to be 13 heads over 20 goes. It's 7 over 20. Then it's 13 over 20. It's 17 over 20. 30. Because again, there's 30 flips. 18 over 40. 22 over 40. 24 over 50. 26 over 50. Okay? All right. Basically, now what they're asking is they're saying, okay, so one of the questions they're going to ask for this one is basically, is a relative frequency of 0.35. So if your relative frequency is 0.35, is this more likely after 20 flips or 50 flips? So think about that. So here, our relative frequency, this is going to be 0.6, 0.4, that's 0.65, 0.35, 30, that doesn't divide in, unfortunately. That's going to be 43.33, 56.66, that also 9 over 20, so 45, so 0.45, 0.55, and then that's going to be 0.48, 0.52. So we can see there that now what we're being asked is basically, would you expect a relative frequency at 0.35 to pop would be more likely after 20 flips or more likely after 50? So even though we do get 3.5 after 20 flips here, that's not what they're asking. They're just asking, if we ran this experiment 100 times, would you expect to have more relative frequency of 0.35 popping up at 20 flips or 50? So again, you can pause the video and think about it. The answer is obviously 20. Because if I asked you, what's the chances if I flip a coin, I get heads? You'd say 50% or 0.5. And the probability of me getting tails is also 0.5. So you'd expect that a relative frequency of 0.35 is quite a long ways away from 50%. So basically for that to happen, you'd want to have a few flips, because the more flips you have, the more likely it is that the relative frequency will approach 50% each. Okay, so if you did 1 billion flips, you'd expect that it would be exactly, or like very, very close to 50% each. So the more you do something, the more likely you're going to get to the true probability of it, okay? But of course, we're only working with probabilities, so we actually don't know what's going to happen. So if you only flip something 10 times, well, you could get 10 heads or you could get 10 tails. But if I did 100 times, there's no way you'd get 100 heads or 100 tails, assuming the coin is fair and not, you know, biased or weighted differently, so it'll land on a certain side, you know. So yeah, that's kind of that. Okay, so that's all you really realistically need to know about relative frequency. Okay, now moving on to sets. So sets are often used in probability. So one thing that I want to look at is if two events are mutually exclusive. So if we have something like this, if they are mutually exclusive, what does that mean? That basically means that they can't happen together. Okay, so the probability, so E intersection F is just equal to the null set. So it just can't happen. That's all. So if we look at the probability of E and F happening, you'd basically have E being over here and then F would just be over here. So there's no chance that they'd happen together. So something like this would basically be like a coin flip. So obviously if I land on heads, I can't land on tails. So they're mutually exclusive events. The same thing of if I roll a dice, getting an even number and getting a 3. They're mutually exclusive. They can't happen together. So that's all. Okay. And now we have a very, very important formula, which you're probably better off knowing. The probability. Sorry, this is another thing that I never said. But all of these ones now, we actually don't have that. It's these actually typically aren't in the log tables, so you will need to know them. Okay, so these are ones that you actually do need to learn off. Okay, so the probability of E union F. So remember, this is E or and F is equal to the probability of E plus the probability of F minus the probability of E intersection F. Okay? And this is basically this picture. Okay? So you have E, you have F. Obviously, if I get the probability of E, I have this. If I look at the probability of F, I have all this and the middle. So what I've done is E union F, this thing here, this is equal to this. So if I add the probability of E and the probability of F, I've added the center part twice, and therefore I need to minus it off here. Okay? And that's it. All right? Okay. So another thing is just how do you calculate the probability of E or F? And basically you just say, let's say we're doing, you've 52 cards in a deck. This is a thing to remember as well. The jokers are not included in this. Okay, so when you're doing probability, the jokers are always excluded. Okay, so you've always 52 cards, not 54. And it'll say, okay, what's the probability of getting a jack? You'd say, well, the probability of getting a jack, how many cards? You've 4 jacks, there's 52 cards, and therefore the probability of getting a jack is 1 in 13. Okay? Now, one thing you will have to be careful of is the probability of getting, okay, I might just do all of it. What's the probability of getting a spade? Well, there's 13 spades in 52 cards, so it's 1 in 4. Of course, there's going to be 1 in 4. There's 4 suits, and therefore a spade is 1 suit, so therefore it's 1 in 4. What about the probability of getting a red card? Well, you've diamonds and hearts are both red, so there's 26 red cards divided by 52. So there's a 1 in 2 chance that you'll get it. Okay? What about the probability of getting a jack or a spade? This one you will have to be careful, because how many jacks are there? There's 4. How many spades are there? There's 13. So you might think, oh, it's 4 plus 13 divided by 52. No. No, it is not. You have to be very, very careful. Why? Because one of the jacks are a spade. Okay? So one of the jacks actually, you have a jack that is a spade. Okay? So basically you're after counting that jack here and here. So you need to do 4 plus 13 and minus 1. Okay? Because there's 13 spades, including the jack, and then there's 3 other jacks. So it's 3 plus 13. Okay? So it's 16 over 52, which is 4 over 13. All right? And then that's kind of the last one. Okay, so just be careful with that when you're doing the probabilities. All right. So here now it says we're going to do one Venn diagram question. So here you have E, here's F, here's U, you have 0.4 out here, 0.3, 0.2, and then 0.1. So again, notice that all the probabilities will add up to 1, okay? So now it says, write down what is the probability of E. The probability of E is just 0.1 plus 0.2, which is 0.3. The probability of F is just 0.2 plus 0.3. The probability of E intersection F is just the thing in the middle, which is 0.2. The probability of E union F, that's going to be 0.1 plus 0.2 plus 0.3, which is equal to 0.6. Now remember, we had a formula for the probability of E union F, so we can also calculate it using this. So just to make sure the formula works, you can also say it's the probability of E, which is 0.3, plus the probability of F, minus the probability of E intersection. So 0.3 plus 0.5 is 0.8, minus 0.2 is 0.6. So again, you would have gotten the correct answer either way. All right. Okay, so those I don't think are too bad. As long as you know them, I think you're fine. Okay. Now I will do one of the questions here because I think 1 or 2 of them can be quite hard. Okay. So here it says the probability of B is 0.8. The probability of A intersection B is 0.3. The probability of A complement is 0.6. So remember, the probability of A complement is everything outside of A. Okay? And it says, what is the probability of A and the probability of A union B? So again, the easiest way of doing these ones, guys, please just draw it out. It is so much easier to see what's going on the second you draw it out. So remember, there's going to be 4 different areas. You have what's here, what's here, what's here, and then what's outside. Okay? So, first of all, you have that the probability of A intersection B is 0.3. Grand. So you have a 0.3 that goes in here. Perfect. The probability of B is 0.8, which means this has to be 0.5. Because the whole thing is 0.8, and therefore 0.3 plus 0.5 is 0.8. You're told that A complement is 0.6. A complement, that means not here and not here. So this and this have to be 0.6. The top one is 0.5, and therefore this is 0.1. Okay? And obviously then you say, well, okay, that means that this has to be 0.1. Why? Because if you add all of them up, you have to get 1. That's a very important thing to remember, that if you add up all the probabilities, you need to get 1. Okay? Okay, so then it says, find what is the probability of A. So the probability of A is just 0.1 plus 0.3, so 0.4. What is the probability of A union B? Well, that's just 0.9. So 0.1 plus 0.3 plus 0.5, that's 0.9. And then it says verify that the probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. So let's see, does this equal to 0.9? So the probability of A is going to be 0.4. The probability of B is going to be 0.8 minus the probability of intersection. The intersection is 0.3. And that is indeed 0.9. Okay? All right, I think that's probably okay. I don't think this stuff is too important. Yeah, I'll just do this bit and then I think I'll leave it at that. Okay. So this is, again, a very hard thing. It's probability given something, okay? So basically, it's like conditional probability is what it is, the way you put it. It's it says, okay, what's the probability of this thing happening if you know this thing happens? Okay, and the way you write it is the probability of A given B. So basically, what this is saying is that what's the chance that A happens if you know that B happens? This is equal to the probability of A intersection B divided by the probability of B. Okay? All right. So one of the ways to do it is something like this. Okay? So here's your Venn diagram. We have X, which is 0.3, 0.2, and Y, 0.1. Sorry, the 0.4 goes out here. This should be a 1. And that's a Y. Okay? So now it says, what's the probability of X given Y? So Y happens. What's the probability that X also happens? You'd say, okay, what's the chance that they both happen together? Chance that they both happen together is 0.2. And you divide it by what's the chances that Y happens? It's 0.3. The reason you're dividing by the chance that Y happens is because in the top one, you're still calculating, oh, we don't know if Y happens. But we do. And therefore you need to divide it by the chance that Y happens because it does happen. It's like saying there's a 50% chance that it happens, but you know what happens, and therefore there's a 100% chance that it happens. So how do you get, if you're at 50%, how do you go back to 100? You divide by 50%. So if you have a 50, you divide by 50, and therefore you get back up. So that's basically what's happening here. Okay? So this is just 2 and 3. So there's a 2 and 3 chance that it happens if we know that Y happens. And then the probability of Y given X, that's equal to, again, 0.2 divided by what's the chances that X happens? X is 0.5. So it's just a 2 and 5 chance. Okay? And remember, these things may not be equal. They might be equal, but they don't have to be. Okay? All right. One of the things here that I want to do is definitely when it's like a boy and a girl, because I think that's okay. Yeah, which these ones are quite hard, and I'll do, yeah, I might do one here. Yeah, I think I'll do 2 questions and I think I might leave it. Okay, so it says, A and B are 2 events that the probability of A is 3 over 10, the probability of B is a half, and the probability of A union B is 3 over 5. Okay? So you would say grand. So do your Venn diagram. You've A and you've B. So this is equal to 0.6. So there's a 0.6 that goes in here, here, and here, and therefore it's 0.4 is the chance of it not happening. Okay? So now you say, oh, well, okay. So the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection. That's how I'm going to figure out what goes in the middle. Okay? So it says, okay, so this is going to be 0.6. Is going to equal 0.3 plus 0.5 minus this. It has to be 0.2. Okay? So this thing is equal to 0.2. So there's a 0.2 that goes in the center. That means a 0.1 goes here, and then a 0.3 goes here. So now they basically say, okay, well, what's the probability of A intersection, A given B? Again, what's the chance that they both happen? That's 0.2. What's the chance that B happens? That's 0.5. So it's just 2 and 5. And now what's the probability that B happens if you're given A? Again, it's 0.2 divided the chance that A happens is just 2 and 3. Okay? All right. Okay, let's do question 20 now. And this is kind of when it comes to like the children, it's actually quite hard. Okay, so you know what? I might actually ask this a different way. Okay, so sorry, I'm not going to bother using the book. I'll just do one more question and I'll leave it because this is a question that actually caught me. So think about it, because it's not half as easy as what it seems. Okay, so if I said, all right, so you have parents and they have 2 children. If the first one is a boy, what's the chance that the second one will be a girl? Okay? And you might sit there and you'll say, well, it's surely 50-50, isn't it? No, it is not. And this is actually very, so one of them is, okay, if you said 50%, you're actually correct. Sorry, I need to phrase this properly. So I'm not saying that the first one is a boy. Sorry, I'm saying if a family has 2 children and I tell you that one of them is a boy, what is the chance that the other is a girl? Okay? So, well, first of all, you do your probabilities. You say, okay, well, there can be 2 boys. There can be a boy and a girl. There could be a girl and a boy. Or there could be a girl and a girl. Okay, so there's a 1 in 4 chance of this happening. There's a 50% chance that they'll have one of each. And again, there's a 1 in 4 chance that they'll both have girls. So now, what I'm asking is, I'm saying, what's the probability that one is a girl? So I'm basically asking for 1 boy, 1 girl, given that 1 is a boy. So if 1 is a boy, then basically you get rid of this. Sorry, that's actually the one that you don't get rid of. Sorry, you get rid of this because you know that one of them is a boy, and therefore you get rid of that. So now you say, okay, what's the chances that I'll have 1 girl and 1 boy? Well, the chance is a half. And you divide it by how many of them have a boy. It's going to be 3 out of 4. So remember, this is just 2 out of 4. So it's actually 2/3, not a half. So that's very important that I express that question properly. So I'm not asking, okay, if the first one is a boy, what's the chance that the second one is a girl? Then it would be 50-50. I'm not saying the first. I'm saying if you know that one of them is a boy, what's the chance that the second is a girl? It's much more likely. Okay? Because you've gotten rid of both of them being girls. So there's only 3 options left, and only 1 out of the 3 have boys, 2 out of the 3 have girls, and therefore it's 2/3. Okay? So that's actually quite interesting. That if I tell you that there's a family and then one of them, and same thing, if I said that one of them is a girl, what's chances that she has a brother? It's actually 2/3, which is very interesting. But it's actually quite, common that, like, if you're talking to someone, let's say one of your friends and they're a girl or a boy, and you ask them, you say, oh, what are your siblings? And they say they have 1 sibling. There's actually a 2/3 chance that it'll be of the opposite sex, which is quite interesting. But that's one of the things that given probably, because you're given new information, okay, and therefore you can get rid of some of the probability because you know that it doesn't happen, and then you can say, okay, well, what's left now? It's actually left that there's 2/3, so 2/3 of the options now have 1 girl. Okay, because remember I asked what's chances that I get 1 boy, 1 girl. I've gotten rid of this probability, so I'm only left with 2 out of the 3 have a boy and a girl, and therefore my probability is 2/3. Okay, so that's one thing to just be careful with, that in probability, that sometimes the answers are very obvious, but sometimes they're not. So it's very important to use the formulas that you're given if you're any bit not sure. Okay? But yeah, no, I think I will leave that there for today, and then I'll move on to probability the next day. But for now, I think that's the rest of probability, I suppose, and the next day. But I think for now that's good enough. So thank you very much for paying attention, and hopefully that made sense. And I'll see you in the next video. Thanks.